All right, great. Thank you all for sticking through to the end here. My name is John Toman. I'm from the University of Washington. I'm going to be talking today about work I've been doing with Dan Grossman on Staccato, a bug finder for dynamic configuration updates. So software configurations are ubiquitous, and you can find them in several different flavors, from compile time flags, configuration files, and command line options. And these different flavors form a spectrum in how easy they are to change. Today I want to talk about what lies at the end of this spectrum here, what we call dynamic configuration options. Now, these are options that can be changed at runtime and do not require a restart of the program for these changes to take effect. You can find this in desktop software, server software, and even in distributed systems like Hadoop MapReduce. Now, these options are the key to supporting robust, long-running software that can adapt to changing user needs. Unfortunately, dynamic configuration updates, or DCU, is difficult to implement correctly. This was a bug in Solr, a text search and indexing server, that was caused by a defect in an underlying DCU mechanism. And as the bug description suggests, the defect caused Solr to only partially apply a requested configuration update. In addition to being hard to get right, DCU is hard to implement at all. This was a comment also found in Solr, left by a developer, expressing uncertainty about how to react to a requested configuration change. Now in this talk, we're going to look more at this former problem, that is DCU is hard to get right, but in our paper we also show how we can extend our technique to help developers implement DCU from scratch. So why do we even need to look at this problem? Maybe bugs like the Solr example from the previous slide are easy to track down and fix. So to track this bug down, you actually have to trace the flow of the schema object as it flows through field assignments, constructor calls, method invocations, until finally, let's see, it reaches this point here when the problematic analyzer is finally unwrapped, but then it flows through several more constructor calls and method invocations until finally it reaches this point where the bug actually occurs. And if this was hard to follow, this is not because it's the last talk, but because actually finding and tracing these bugs in practice is quite difficult. And so that's why we've developed Staccato, a technique for automatically finding bugs and dynamic configuration update mechanisms. So for the rest of the talk, we're going to first discuss correctness conditions for DCU implementations. Before we can say how we find bugs, we have to first say what it means for an implementation to be bug-free. We'll then discuss how we can check for violations of these correctness conditions using a dynamic information flow analysis. We'll briefly discuss our implementation of this analysis in a tool for Java programs called Staccato, and then finally discuss our results of applying Staccato to 3 open source Java applications. So Staccato actually offers 2 alternative correctness conditions for DCU implementations. As we'll soon see, we found there was no one-size-fits-all when it comes to specifying correctness for DCU. So let's start with a simpler example. The Solr bug is not our working example. Here we have some request wrapper that allows the user to configure the username and token that are sent with each request. Notice, however, that the token option is cached into this token object field, whereas the username is reread on every invocation of the send request method. And this is going to be a problem because if the token option is changed, then this token field will become out of date or stale with respect to the underlying program configuration. And this is very similar in form to the Solr example, where an object field was not updated in response to a configuration update. And so this motivates our first correctness condition, which states that an execution may only observe values derived from the most up-to-date version of the program configuration. And this is a good condition that is sufficient to find several interesting bugs. So why do we need a second correctness condition? Well, here's another example where we have some spot service whose main functionality is to echo back phrases of the form, let's say, run spot run or bark spot bark, where the verb in this phrase, run and bark, can be configured with this verb option that is set with this set verb method. Now notice that we have 3 configuration accesses, 2 reads and 1 write, that are not protected by any synchronization. This will be problematic. So to see why, let's consider the following scenario with 2 threads, T1 and T2. T1 begins by executing a read of the verb option and then stalling. Thread 2 then begins executing and updates the verb option to some new value. Now when thread 1 resumes, it'll read this updated value. And now when spot request returns, it'll return the string run spot bark, which violates our intuition about how the spot request should behave. Now the good news is that the first correctness condition will actually flag this result as an error because it is partially built from an out-of-date version of the verb option. So why the second condition? Well, let's consider a variation on the same scenario, again with 2 threads, but this time thread 1 executes both reads of the configuration option and receives the same value each time before stalling immediately before returning. Then thread 2 begins executing, performs its configuration update, and now when thread 1 returns, it'll return the string run spot run, which seems like it would be intuitively correct, except that the first correctness condition will deem this result an error because it is built from an out-of-date version of the verb option. But this is very unsatisfying. We'd like to allow intuitively correct interleavings like this for performance reasons, while still ruling out inconsistent results like the one we saw in the previous slide. And so this gives us our second correctness condition, which states that a method execution may observe only a single version of each configuration option, not necessarily the most up-to-date version, but some single consistent version. Now together, these two correctness conditions form a specification of how our program may behave in the presence of dynamic configuration updates. But which one of these correctness conditions is appropriate is necessarily application dependent, and so we have the programmer specify a default correctness condition for the entire program with the option of fine-tuning the correctness condition on a per method or per class basis with annotations. Now looking at these conditions, we can already see a lot of commonalities between them, and so this gives us an intuition for how our approach will work. We will version the configuration options of a program and then track configuration values as they flow through the program. So let's make this a little bit more concrete. Staccato is a dynamic configuration-aware information flow analysis with three main parts. First, it versions the configuration of a program. It tracks configuration values and their versions as they move through a program. And then finally checks for violations of the correctness conditions. So to see how this technique works, let's see how Staccato operates on a simplified version of the spot service bug from earlier. This example will show how Staccato conceptually works. Later we'll see how to make it more efficient and how to extend it to detect more exotic types of bugs. So the first piece of Staccato is to version the program configuration. So Staccato maintains this version map, which associates with each configuration option a version number. And here the verb option is given the version number 3. Staccato also tracks configuration values. So when the verb option is read here and stored into V1, V1 is going to be tagged with this piece of metadata. This is called V1's configuration history. In general, a configuration history for some value, let's say X, is a mapping from the names of the options used to build that value to the versions of those options. Now for many values, this mapping will be empty, which implies the value does not depend on any of the configuration at all. So when the verb option here is updated, not only is the value updated in the underlying configuration abstraction, but Staccato automatically increments the version number, which captures that we now have a new version of the verb option. Similarly, when the verb option is read here and stored into V2, V2 is tagged with the configuration history that contains the version 4. And this captures the intuitively obvious fact that V1 and V2 now hold two different versions of the same configuration option. Now we know from experience that this concatenation here is problematic, but for Staccato to detect this bug, R's configuration history somehow has to reflect the history of V1 and V2. And we see that Staccato automatically handles this, and R's configuration history maps the verb option to the set containing 3 and 4, which captures that, again, R is built from versions 3 and 4 of the verb option. And in general, Staccato conceptually combines configuration histories with pointwise set union. So now we know that we have a violation of both correctness conditions, so the final piece of Staccato is actually detecting this violation. Staccato checks for violations at key program points, specifically on variable reads, field reads, array reads, arguments at method entry, and when a value is returned from the method. So we know where Staccato checks for violations. Let's look at how. To check a value for a violation of the staleness condition, it suffices simply to check the value's configuration history to see if it contains any out-of-date versions for any configuration options. If it does, as is the case in this example, then the value reflects a stale view of the program configuration and violates the condition. Similarly, for the consistency condition, it suffices simply to look to see whether or not there are multiple versions for any option in the history. If this is the case, as again is the case in this example, then the values get inconsistent. So the technique we just saw was effective but very inefficient. We're storing multiple sets for each program value, so our shadow state is very large. However, we can actually still effectively check for violations using only a single integer per option in the configuration histories. And to see why we can do this, let's look again at our correctness conditions. So the first condition, staleness, asks whether there are any old versions in the history. But we can actually ask an equivalent question, which is what is the oldest version in the history? And we can do this because it doesn't actually matter whether or not there is a more up-to-date version, only that the history contains some older version. Similarly, for the consistency condition, it doesn't actually matter what precise versions are stored in the history, only that the size of these sets here is greater than 1. So for neither of these correctness conditions do we need this full set of values here. So the restated staleness condition leads to a straightforward way of compressing this information. Do not store this full set of versions, but only the smallest version in the original history. And this is sufficient still for checking for violations of the staleness condition. Unfortunately, it is insufficient for finding violations of the consistency condition. And remember, to check this, we had to look at the size of these sets, but we've since thrown away this information. So to overcome this, we add an extra little bit here to the compressed representation, and this is what we call the consistency flag. And this flag is set precisely when multiple versions have been combined in creating the configuration history. So given this definition, it's now very easy to check for violations of the consistency condition. The consistency flag is set precisely when the condition is violated. So the only missing piece now is how Staccato combines these history representations. We can no longer use this conceptually simple set union operation I described. So to see how it works, let's look at an example. Here we have the old representation that are being combined with set union. When we apply the compressed representation to them, the first input history maps the foo option to the tuple 1 and false. 1 is necessarily the smallest version, and because the original history is consistent, the consistency flag is unset, and a similar argument holds for the second input history. When we combine these two, the compressed output representation maps foo to the option version 1, which is the smaller of the two input versions, and now the consistency flag becomes set because we're mixing two inconsistent options. In this scenario, we're mixing two consistent options and the consistency flags are both unset, so the output consistency flag is still unset. But in this scenario, even though we're mixing two consistent version numbers, one of the input consistency flags is set, so the output consistency flag is also set. So now I'm going to talk about how we can extend Staccato to detect more exotic types of bugs. As we saw in the spot service example, Staccato automatically combined the configuration histories during string concatenation, and in general for all of the primitive operations, Staccato combines the histories of the operands to give the history of the output value. But what about this scenario? The variable C here clearly depends on the username and password options, but relying only on information flow at the primitive value level will fail to capture this relationship. So you can imagine unconditionally propagating information across method boundaries, but this leads to a large loss of precision in practice. So what we do instead is that we have the programmer add these Staccato propagate annotations to methods. And these methods signal to Staccato that the output of the method should reflect the configuration history of its inputs. Now, for the purposes of propagation, there are two possible outputs. For methods like this then, we have the return output, which simply combines the history of the input arguments to give the output of the returned value. For side-effecting methods such as this one, we also allow for the receiver output, which simply combines the configuration information of the input argument to give the history of the receiver. So finally, I want to discuss inconsistencies that can arise due to control flow. So in this example, if the op configuration option is changed while the loop is still executing, then the output variable here can be inconsistently processed. But Staccato will fail to detect this, as we described it so far, because output only indirectly depends on the op configuration option. Now, one way to detect this would be to precisely track control flow dependencies dynamically. Unfortunately, this is simply intractable and does not scale to the size of programs that we are interested in evaluating. So instead, as we apply heuristic, we require that every method execution observe only a single version of each configuration option. We do this by maintaining the Sentinel sigma history, and this is the method execution's configuration history. Unlike a regular values configuration history, which records the options and the versions used to build a single value, this history records the options and the versions used to execute the entire method. So whenever a value is read within a method, that value's configuration history is merged with the method history, and that resulting history is then checked for inconsistencies. So let's see how this works. When we read the op option here, the value returned will be tagged with some version number. Let's say it's 1 here. This history is then immediately merged with the configuration history of the method to give the history we see on the slide. At the end of this loop, the op option is updated, let's say by some other thread, and we return to this point and we read the op option again, we will get some value with an updated configuration history that has a new version number, let's say 2. When we combine this history with the existing method history, then we receive an output history with the consistency flag now set, and this signals a possible control flow inconsistency. So in review, Staccato versions the configuration of a program. It tracks configurations using configuration histories attached to program values, and we also allow for detecting and expressing more exotic types of bugs by allowing information flow at the object level and using an unsound but effective heuristic for control flow tracking. So I'm now going to very briefly talk about our implementation. Staccato is a two-step process. First, an annotated program and libraries are pre-instrumented with this phosphor tool, which adds primitive information flow tracking for values and arrays. This intermediate program is then fed into the Staccato instrumentation tool, which adds code to perform the checking and information propagation. And then this instrumented program is then run on a stock JVM with a small runtime library. So now I'm going to finish up and talk about our evaluation. In evaluating Staccato, we are interested in 4 research questions. First, does software with dynamic configurability suffer from violations of our correctness conditions? Are DCU errors a problem in practice? How effective is Staccato at finding these errors? For some real applications, what is the burden of using Staccato? And then what is the performance overhead of using Staccato? So to evaluate Staccato, we looked at 3 open source applications: OpenFire, Subsonic, and JForm. These were all non-trivial programs of approachable complexity that also offered high levels of concurrency and dynamic reconfigurability. So what about Solar? We did not perform a full evaluation on Solar because Solar was close to 500,000 lines of code. And there's no technical limitation here, but using Staccato requires some familiarity with the code base in question, and 500,000 lines was beyond what even a very, very motivated graduate student could perform. But we did perform an informal evaluation where we showed that our technique was sufficient to find the bug in the introduction. To evaluate Staccato, we annotated and ran the evaluated program on the JVM with the Staccato runtime library, and then ran several test clients in other separate JVMs. These test clients executed functional tests developed by us that exercise the core functionality of the software under test. And these actions involve posting polls and queuing some song or messaging some other user on the service. Alongside these test clients, we also ran Havoc clients. These clients exercise the built-in administrative interfaces found in all of our evaluation targets to introduce randomly selected mutations of the program configuration while the test clients were running. And these mutations involved enabling or disabling some feature, or maybe changing the locale of the software or the encoding of the output. If the Staccato runtime detected a possible error, it logged its findings, and we classified these results offline. So we found bugs in all of our evaluation targets. For OpenFire, most of the staleness violations that we found were the result of this very problematic update idiom, where we have this configuration value that is being updated in the underlying program abstraction and then cached into an object field. But this isn't done atomically, so that the audit IQ field here become out of date with the underlying software configuration. And this error will be caught on later reads of this audit IQ field. JForm also has an almost degenerate version of the inconsistency bug. So here we see this page title option that is being read twice with no synchronization, and it's being used to populate two different response parameters. Now, to find this bug, we had to add propagation to the receiver context variable here. And to find many of these bugs, we actually had to add this propagation annotations, but we need only about 30 of them for the over 100,000 lines of code in our evaluation. I should also mention that the one false positive we discovered was under very similar circumstances, where we had two reads of the same configuration option, but it populated the same response parameter with no interleaving reads. And so Staccato was not able to detect that any inconsistency was actually concealed by this. So to evaluate programmer effort, we looked at the number of annotations we had to add and the total number of lines changed that we had to perform. Many of these total lines changed is because the configuration abstraction update code has to be integrated with the Staccato runtime library. But in general, the number of lines we had to change and the number of annotations were very low for Subsonic and JForm. OpenFire had 100 annotations, but this is because OpenFire also had 250 annotations. So you can think of the annotation burden as sort of growing linearly with the number of configuration options in your program. Also, the large number of total lines changed here is because we experienced extensively with Staccato's update support using OpenFire, and so many of the lines of code changed there are the result of those experimentations, and I invite you to look at the paper for details on that. Finally, we looked at performance update. We looked at the overall slowdown experienced and the total memory overhead. So we looked at the average slowdown experienced by the test clients when executing some test action. So on the left here, we have the slowdown experienced on JForm when sending a private message to some other user. And the geometric mean of this gave us our overall slowdowns. And these were 5.3, 2.11, and 1.2x respectively. And our memory overhead was also less than 2x. And this is generally competitive with other dynamic analyses. So to wrap up, a lot of research has gone into looking at program configurations, but most of this work has assumed static configurations and looked at trying to infer what configuration options do or guiding the programmer or user to the correct configuration or diagnosing some crashing run that is the result of a bad configuration. And to our knowledge, we're the first ones to look at this problem of dynamic configuration updates. Another interesting related line of work is in automatic atomicity and linearizability checkers. The bugs that these tools seek to find are very similar to violations of the consistency condition, but to our knowledge, none of these tools can handle the multiple interprocedural interacting objects that our tool can find. So in summary, Staccato, we defined correctness conditions for DCU implementations. We also developed a technique to detect DCU bugs, and then we found DCU bugs in 3 open source applications. Okay, thank you very much, and I'd be happy to take your questions.
Hi, how much do you think this could be solved just programming, sort of as a comparison? Like, suppose you just had a really good library. Anytime you want to change the configuration option, so that's sort of your competition. And how does it compare to that?
Exactly. I think that what I found is that you can write the best configuration library in the world, but once the value passes out of your library, you have no control over it. And it's sort of hard to influence how the programmer will eventually use your library. There was actually a talk at Kurion about a library that works very hard to help you get consistent configuration updates across your node by doing these atomic swaps of your configuration at some point. But I spoke to the author afterwards, and I asked him what happens if this swap happens in between two reads. And this was not something that he'd accounted for. But we talked about it and we agreed that there has to be some sort of programmer help. You can't solve this purely with libraries or a good configuration library. It can get you part of the way there, and it's certainly, using a better library is better than what we found a lot of people do, which is just use some global hash map and then just put the new value in there without any care in the world. But you do need some defensive programming on the part of the programmer. Great question, though.
I was curious about one thing in the evaluation. Did you have a way to force extra context switches between the Havoc threads and the main threads? Like more than would happen normally?
Yeah, so sure. We had sort of. We actually added some randomly selected very short sleeps. It would sort of read the value and then sleep for a very short amount of time to try to induce these sort of pathological bugs. Because some of the bugs we found, a lot of the bugs we found did rely on concurrency. I should mention that not all of the bugs did rely on concurrency. And I invite you to look at the paper there for descriptions of those bugs. But since some of them were relying on concurrency, we did do, I think, what's the standard technique of having some threads sleep randomly to try to help induce these problematic interleaving.